Hi, everybody. I'm Brian McKay, and I was recruited here by the Lions some 24 years ago to actually study age-related macular degeneration. And the Lions have bought the equipment a large portion of the time. We had the Lions Eyeball Express, so the tissue that I studied to do AMD research was all part of the team. And the Lions Club has been a team player for the McKay Lab for a very long time. In fact, it's not really the McKay Lab; it's our lab. We've done all of these things together, and most recently, I'm going to show the data that we just took to an international presentation with one of my students, Serena, who is an undergraduate student, and she presented this at an international presentation. We had 12,000 people there from countries across the world. So she was a little nervous. It was a little scary the first time you do something like that. But what we're doing here is we're trying to figure out and get to the cure for age-related macular degeneration. We've had several iterations. We're in our fourth round of clinical trials. But the bottom line is we're still doing work because we haven't fixed it yet. And we can help people, but only about half the people we have no response. So part of what I'm trying to figure out here in this poster is, what am I missing? Why are we not helping everybody? Why are we only, say only, well, it's the number one cause of blindness. If I only help half, that's pretty good. We're doing good work. Unless you're in the other half. And I always get the feeling I'd be in the other half. So what we have here is we're looking at trying to figure out what pieces are necessary for us to have the effect. And so the primary drug that we've developed is L-DOPA. And we discovered long ago that L-DOPA, which is a medicine for Parkinson's disease, although it's been given to people since the 1960s, nobody knew until we discovered in the 2000s that there was actually a receptor for L-DOPA in all pigmented cells. So age-related macular degeneration is race-related, and if you're Caucasian, you have an 8.1 times greater frequency of developing disease than if you're in any other race. So that tells me that that receptor has something to do with the disease. So we discovered the receptor. The ligand for the receptor was L-DOPA, and we tried that, and it works, but it only works in half the people. So now we're trying to figure out what's happening. And in this experiment, in this series of experiments, we're using two different species. We have porcine eyes, which we can get, and then we have human eyes, which we actually get from a lion's eye bank. And the Lions have been very good about providing eye tissue and helping us get that tissue, because without that tissue, I can't solve AMD. AMD is species restricted, meaning that it really only happens in higher primates, and the majority of the tissue that I can actually get in animal eyes, and what we're using here, is actually porcine, pig. So I can't use pig really to study age-related macular degeneration. The other thing about pig tissue, and we'll get to this later because it's important, is that it's from young animals, right? So we don't have 30-year-old pigs. We don't have I don't think 60-year-old pigs exist. And we're studying aging disease in animals that are roughly 4 months of age when we get the eyes. So there are some issues here that we're trying to figure out, and there are some ways in which we treat the cells to try and separate out issues that may affect how the drug works. Remember, we're using a drug called L-DOPA to cure an age-related disease in humans, and it works, but only in half the people. So trying to do this in pigs is a little tough, but we're making progress. So one of the things that we've shown long ago now is that part of the process is the release of these small things called small extracellular vesicles. We used to call them exosomes. They've changed the names now. But we isolate and purify these, and we're using, to do that step, is actually using centrifuges that were provided to us during my startup, actually, from the Lions Club. So if you come to my lab, you'll see these big blue lion stickers. They are on they are on the machines that I use to actually do this work. So the Lions has really been and is still continuing to be part of what we're doing. So here, if we look at these right here, we can see that hypoxia, which is in the purple, and the red has no different. Hypoxia is a lack of oxygen. And as we get older, in the eye, in the back of the eye, there's a component of lack of oxygen, hypoxia, that is happening because the blood vessels start to die out around the same time AMD starts to occur, hypoxia starts to occur. So what we're looking at here is, does L-DOPA or treatment change with hypoxia? And the answer is no. Hypoxia does not alter the effect of L-DOPA. So then we look and we're trying to see in different ways and get to the end quickly. We showed that it isn't necessarily hypoxia, it's whether the cells are activated to divide. So it's proliferation. In cells that are hypoxia, we have no difference with L-DOPA, but in cells that are stopped dividing, there's an enormous difference. And that brings us to where we are with human RPE. Because remember, human RPE from human donor samples that are 80 years old, they haven't divided since the 4th month of gestation. Those cells have not divided since before these people were born. And so it's proliferation, and what we're showing right here is this change is mimicked. We can go back to making L-DOPA work, which is dropping these, if we stop the cells from proliferating. So the end point of all of this work right here is to say that we can redo this, and we figured it out. It's a lack of proliferation. If the cells are proliferating, nothing happens, but if the cells stop proliferating, we get the effect we need. And we can use this new data, this new information, to better treat humans with AMD. And that's actually the goal. Thank you.